All right. Hello, everyone. Hope you can all hear us on Zoom. Yeah, I will take care of that.
That would be that mouse.
That one.
That mouse.
All right. So we have to chase the right mouse to take care of it, and then I will start this on my own computer to monitor the room. So okay. All right. So we made it work. That's great. Welcome everybody. My name is Danny Shaw, your host today. So we are having another engineering seminar series today. So we're very happy to have our longtime friends, so big supporter to our program, Mr. Brian Roper, come from Wisconsin DOT. So he's gonna present a project, very structure-wise, I would say, structure-based, and then very high profile in Green Bay. I'm very happy it didn't happen recently, right? It was a while ago.
Oh yeah.
But it's a great lesson for us to learn. We're very happy. So I'm very proud to do a quick bio introduction of Mr. Roper. Pay attention to it. So this is a good model right here for you to learn from. Mr. Roper is a transportation engineering manager with over 3 decades of experience in both public and private sectors, including over 18 years at DOT. Over the course of his career, he has performed and management of a wide variety of traffic, planning, enviro, design, construction, consulting. That's everything, isn't it?
Pretty much.
Everything civil, environmental, and engineering touches, right? So since 2020, he has led the system operations section in Southeast region, which encompasses the Milwaukee region, Kenosha metropolitan areas. How many population you have? That's a
Lot.
That's a lot, right? So, and then with 55 dedicated professionals, Wistar is Wistar's largest section of engineers and specialties. This project, the projects included single operation maintenance, lining, safety, signing, marking, operation, modeling, work zone, roadway maintenance. So in other words, Mr. Roper is in charge of your safety. So, right, that's our definitely ultimate goal for transportation engineering, right? So, Brian has led multi-billion-dollar freeway expansion programs, large bridge reconstruction and repair, and also statewide consulting service. He's an alumni from Iowa State, and also a master degree from Purdue, focused on transportation. So he's a registered professional engineer in both Wisconsin and Minnesota. Also, he's very active in ASCE and also ITE. So awesome. Thank you so much for coming here. Please help me welcome our speaker.
All right, thanks. Really appreciate being back on campus. I was actually here about 9 years ago presenting this information, obviously. Certainly wasn't this room. I've been built since then. I have 3 kids that all graduated from Platteville, so very, very familiar with the great, the great programs, the great people that we have. One of my sons is actually working for Michigan DOT as a civil engineer. So, all right. So for those of you who are here, those who are online, again, appreciate the opportunity. So today we're going to talk a little bit. It's honestly, Danny, when I delivered this last time, he told me it was perhaps one of the best ones that he'd ever seen. I'll let you folks be the judge, but it's going to get into a little bit of what was happening in Green Bay. So if I hit page down, please work. I said, please work. Ever so slowly. Come on. Well, this is a really interesting presentation. We're going to spend some time on the first slide.
We have too many screen and computer here right now.
Right, so
here we go. I'm gonna pause this, and then we should be able to move it here.
Okay, perfect. All right. So there's a couple videos, and good heavens, I don't want to lock up the computer. So it all started on September 25th of 2013. So if you can imagine just, an ordinary day, an ordinary conference room at DOT, and then all of a sudden something happens and the governor and the Secretary of Transportation are there to announce the closure of a major transportation artery in Northeast Wisconsin. So for roughly the next 59 minutes, we're going to talk a little bit about that and what really makes this transportation emergency different from, those that we see in the news often, is that for the first several weeks, we didn't know what caused it and what we should do. So we're going to get into touch on several aspects of the Leo Frigo Bridge, which is Interstate 43 up in Green Bay. So here are the four basic things we'll talk about. Get a little, got to orient folks. Obviously, some of you are perhaps even from the northeastern part of the state, so you know where this bridge is, but just to help the rest of the folks. Then we're going to focus on the investigation and the stabilization. So in other words, after the event happened, what is it that we needed, trying to figure out what happened, what's going on, while at the same time working on transportation and life safety. We'll then pivot from that to talk a little bit about the permanent repair, and then kind of wrap things up with touching on a few other things, just a reflection of the overall project management, as well as next steps. So the great people up in the Green Bay area, they had a sense of humor about it when this bridge closed. And so one of the local, is there a room camera view? No, there's not. Sorry. And Danny, how am I gonna, if I can, okay, it'll disappear. Fantastic. Got it. All right. So the good people in Green Bay, they actually came up with an appetizer for that called the Leo Frigo dip. So, all right. So first a little bit, we're going to touch about this to help orient us. One thing I want for not just the folks here in the room, but also online to understand, we're not using some sort of a fisheye lens camera, Photoshop, etc. Every time you look out at this roadway and you see the dip, that's real. That's not exaggerated in any way. It's a 2-foot dip. So again, to get us oriented, some fundamentals talk about what we refer to as day zero, how the emergency relief process comes into place, some of the initial PI and traffic that we had to consider, as well as construction impacts for the US 41 project that was underway. So again, to orient ourselves on the map, the Leo Frigo Memorial Bridge is there at the mouth of the Fox River, where it gushes into Green Bay and ultimately into the Great Lakes. It's in those final couple miles of Interstate 43, which you see kind of wrapping around and then heading down along Lake Michigan to Milwaukee, and then obviously to Rockford. US 41, which is now Interstate 41, continues to the north towards Michigan, also heads to the south, taking a different path towards the Milwaukee metro area. So a few fundamentals about Leo Frigo. Again, keeping in mind, we're talking about 2013. So Leo Frigo opened in 1980. It was called the Tower Drive Bridge. It is a tied arch bridge. That's a special kind of bridge. It has two siblings here in the state of Wisconsin. The Hone Bridge, which is on Milwaukee's lakefront, and the Bong Bridge, which is up in Duluth Superior. Now you're like, wait, aren't all those ports? Yes. That's why there's 120-foot navigational clearance over the waterway so that they can get the bridges, the boats underneath. So Leo Frigo, about 8,000 foot long, couple hundred feet tall, at the time was carrying over 40,000 vehicles a day, which was appropriate for the 4-lane freeway crossing that it was. So like if you ever go into the doctor's office and they're like asking you about your health history, this is the health history of Leo Frigo. Again, born in 80, had a little structure repair in 88, some asphalt overlay, little structural work in 2012, 2013. It actually had been inspected a little more than a year before the event, and it came out fine. So there was nothing in that structure's health history that would suggest that something interesting and devastating was about to happen. I don't know. That's your next question to deal with. I'm going to just roll on. So day zero, September 25, 2013, Pier 22, one of the supporting structures of that bridge, sank 2 feet overnight. And that settling of Pier 22 caused the sagging of the bridge deck across all 4 lanes. So just to orient us again, over to our far left is the Fox River. So that's in essence the middle of the bridge. And this was about 5 piers east of the river. That's the epicenter of the location of the SAG. So on day 0, September 25th, the incident first starts getting reported by into the law enforcement around 2:30 a.m. Within 12 hours, there's a news conference in a nondescript DOT regional office building. The governor and the secretary of transportation flew up there. This thing was carried live all across the state because it's not every day that a bridge sags 2 feet. In fact, arguably, it's something that you almost never hear about. And so it immediately piqued international interest. So, you know, back in the day, if you were watching a network news show, they would probably show like 30 seconds of, you know, meanwhile in Green Bay, Wisconsin, the bridge mysteriously sagged 2 feet overnight. So a lot going on. There we go. Whoops. Okay. Following day in the Green Bay newspapers, obviously front page headlines, just showing again that significant dip, not exaggerating in any way. And so at that moment in time, you know, September 26th is day 1. Most bridge incidents, most transportation emergencies that happen, be they a flood, be they a fire, you know, perhaps somebody left too much traffic control materials next to a bridge and it started on fire and melted it, or a fuel tanker flipped and burned and melted it. What caused this? We had no idea. So therefore, we had no idea of when it would be back open. So clearly, we had everyone's attention in the Green Bay area as well as in the state of Wisconsin. So on the second day, and I think for folks down in the Milwaukee area most recently, but certainly all over the state, whenever we have some type of a catastrophic event that impacts infrastructure, the first step is to get a proclamation of emergency. So on day 2, the governor signed this proclamation, and that's the first step to pursue federal emergency relief funds through the federal aid highway program. Now, they can be used for one of 2 things, which is natural disasters as well as a sudden catastrophic failure like we saw here. Now, one thing that we did as a little bit of levity, but also to underscore the seriousness of the situation, is we actually printed out copies of that declaration. And when, you know, we'd have meetings and people would talk about how like, oh, well, we need more time or we need to check in, we would kind of roll out the emergency declaration and say like, yeah, but we're going to need you to decide in the next hour. We're going to need a decision at this meeting. You know, we don't have a lot of noodling time on it. And so that was very effective. Now, the one thing from a budget tracking standpoint, of course, all of any money that flows in has to be accounted for. And what helped us is that we were already in the midst of the roughly $1.3 billion Interstate 41 reconstruction project up in both Green Bay and Oshkosh. So from that standpoint, we had a lot of the tools and the tracking in place to be able to help us, you know where all the costs were going to. A lot of FHW coordination along the way. And, you know, some of the things that were required in terms of different cost categories, you know, included, of course, just, you know, the flat out cost of construction. But there was a lot of engineering that went into that. In order to help manage the traffic, we had these group of vehicles called a freeway service team that would be out there to help, you know, clear motorists off the road, change tire, you know, give them a gallon of gas and get them on their way. Additional law enforcement support in order to keep things rolling, as well as the detour routes. Some of the detours initially weren't roads that are necessarily built for interstate traffic. And so there was a need to do some restoration of those as well. So in those first few days, as you can imagine, as with any, you know, breaking news story, public involvement was pretty intense. You know, this again is another shot from that initial day 0 conference. And really the focus was on 3 things. You know, Danny actually mentioned it at the front when he was talking about what we do. Number 1 was safety, making sure that we were keeping, the motoring public safe, as well as the individuals who were charged with going in and kind of unraveling this mystery. Also, alternate routes, helping people, even though this major artery's been shut down, to continue to move around. And then underscoring the investigation commitment to repair. So this is not like one of those CSI kind of shows where you're able to just go in and by minute 57, you've got everything figured out. But yet that's kind of the appetite of folks that, we'll be able to just click our fingers and get the answers right away. And so just letting folks know that we were on the case, we're making progress, but, it was going to take a little time. So once we moved past that initial burst of media interest, then it was about, kind of making sure that, people would still have questions. And so recognizing and needing to satiate that curiosity is making time, making availability. So, sometimes we were able to host an event like this out on the actual site, after giving the media folks their appropriate PPEs in terms of hard hats and vests. And then just sharing with them kind of where we were with things on the project, which was, again, important to keep them safe, but important because unfortunately, sometimes if not granted those opportunities, folks will take unnecessary risks that could result in themselves getting hurt or even killed. So again, we were working together, sharing the public interest. There's another briefing that was held up there. So we had 5 news conferences as well as 5 kind of on-site media tours. Sometimes it would be as simple as just, letting folks know, hey, we're going to have somebody from the project there for a couple of hours. Did you want to come in, ask them a few questions, film it so that you could then show it on the news. So definitely a lot of media interest, not just from the Green Bay market, but from the Madison, Milwaukee, and Wausau markets as well. So at the end, the newspaper published a rather positive editorial, just kind of, really praising everybody together who cooperated, worked, and was able to get the bridge back up. And now you're probably saying to yourself, well, Brian, we're like 12 minutes in. That's it? That's all your presentation is? No, we're going to go a lot deeper into a lot more of these issues here. So next aspect of it is traffic and detours. So again, where you see the orange the orange object in the upper right, that's the section of Interstate 43 that was closed. You recall 40,000 vehicles a day. Where are they going to go? So if you happen to be right there, right at the exit where it's closed, and you plug it into an app that didn't exist in 2013, such as Waze or Google Maps or whatever, it would tell you, oh, okay, you just take the blue route. Well, that seems reasonable. But of course, as we'll see, that wasn't necessarily, we were able to accommodate all that well. And so then we had to then focus on some of the more reasonable routes. So this is just a street in downtown Green Bay at about day 1. So again, you take 40,000 vehicles a day running at freeway speeds, and you dump them onto the surface streets. This is what you're going to get: blocks and blocks and blocks of backups. And roughly 10% of them were trucks. Trucks didn't want to be there. Nobody wanted the trucks there, but that's part of the mix. And so we knew pretty quickly that we needed to do other things to get them off the road. And we actually did a back of the envelope estimate that said every day that bridge was closed, it was $140,000 of user delay. So for all those folks that were spending extra time in their cars and trucks, that's kind of that eccentric cost that was associated with it. Highway 41, Interstate 41, part of what, sometimes you're just gonna like fall into luck. And in this case, the luck that we fell into is we were about a week or 2 away from a stage change on that interstate reconstruction, where we were about to take away lanes of traffic on Interstate 41, then US 41. Well, it was as we saw in the previous slide, it was destined to be our alternate route. And so we actually negotiated and paid the contractor to delay that stage change so that we could accommodate more of the traffic on those freeway detour routes. So that large green, orange looking thing, which is not a circus balloon animal, but is in fact, that's all of I-41 that was under construction at that moment in time. Not going to lead the list to you off of the left. Suffice to say, there wasn't many opportunities for us to do anything but put folks on 41. And so anything that we could do, again, whether it was the freeway service team or just, working to delay some of those critical stage changes in order to make the traffic impacts as little as possible. So now we're going to zero in from those kind of traffic or public involvement effects into investigation and stabilization of the Frigo Bridge. So those things in the left, we're going to zoom in on each of those in greater detail so that we really start trying to kind of walk each of you through that same sort of engineering inquiry process. When you don't know what caused something and you see the effect, how you work your way toward ruling in or ruling out different things. So here we are. It's day one. Okay. And part of what we want to do is, of course, do a little recon on the site, look for things that are most obvious, as well as on, not just on the site, we'll call it at ground level, but at the structure level, which you may recall was up to 200 feet in the air, as well as geotechnical exploration. And then as we were gathering this information, working with our partners to test things, to install instruments, to try to get more understanding of what some of those root causes are. So starting with structures, again, your bridge pier just sank 2 feet. You probably should not go rolling up there with heavy equipment. And so we wanted to take a real systematic approach, starting first with, both the structure and the deck. And as you may be wondering what that little device is over to the left, and we'll talk about this again a little later, but part of maintaining safety for the contractors, the engineers, the geologists that were working on the site, we had essentially like these gyroscope kinds of sensors attached to large blaring sirens and lights that we attached to every pier. Again, at the time, we didn't know it's not unlike with an earthquake, when's the next pier going to settle? What's the next thing that's going to happen? And so we wanted to make sure that we had a warning system in place that if it detected movement, it would very quickly and very loudly alert everyone within the area to be able to clear out of the vicinity of that. So again, starting with our core value of safety, we established kind of a red zone near Pier 22. Again, that's the epicenter. We don't know what's going on, so that's the area we want to be the most careful about. Now, part of what we did to determine what additional movement may occur, we set up and started surveying, taking survey points twice a day, just to again confirm in our minds, are we seeing any movement, a little movement, or a lot of movement? Now, this is October right now here. It's raining outside. It's fabulous. So Green Bay is a lot further north and east of here. And sometimes it rains in September. It's not always dry in September. So with the structure inspection came structure inspection challenges. So here's a scissors lift. We were hoping to be able to use on that day, and you'll notice that it's buried axle deep in mud. So a lot of the ground that was beneath the Leo Frigo Bridge included that lovely invasive species known as Phragmites and a lot of other muck. Roadway that wasn't really, I should say ground surface that really wasn't intended to drive on. And so, every day was a learning period or an adjustment of it. So in terms of the structure inspection, they started with the deck, even the part of the deck with the dip in it, and did a physical walkthrough, physical inspection. And, hey, we lucked out. There was not anything unusual. There wasn't any, there was a little bit of cracking, but there was nothing really overtly significant. The joints were all still lining up together. So generally things were in good condition. So again, that comment I mentioned about luck, it was one good thing we like to see. So then we move from the deck down to the superstructure. And once again, no unusual distresses. So, there was certainly a little bit of deformation, but it was in that plastic, in that plastic part of the deformation curve. We hadn't reached the point where things were so deformed that they couldn't be put back. And again, a little bit of paint cracking, but nothing significant. So in spite the fact that the bridge deck had just settled 2 feet, superstructure actually looked pretty good. Not really anything immediate that popped out of it. And so here's another shot. This is obviously from up just in the superstructure from the inspection. As you can imagine, at Pier 22 itself, you would see a little bit of bending because, again, it settled 2 feet. So there's a shot of that. So now that we had kind of examined and cleared the structural aspect of it, it was time to turn our attention to the subsurface investigation. And, again, we undertook a really rigorous regimen of trying to look at what was going on because, the bridge settled. It didn't happen from the top, so there must be something going on. So test borings, looking at groundwater and corrosivity. So even for those civil engineers like ourselves that maybe aren't heavy into the chemistry and biology aspects of it, we're going to be doing a little recollection of what that would look like. Even, and here's just kind of a cutaway there from Pier 21. Kind of, I don't know if you've ever gone into a doctor. Okay, if your parents have gone into a doctor and they run like 25 different tests because they're really not sure what's going on. That's what we were doing because we knew we were on the clock. So it was like, well, what if it's microbes, like actual living cellular beings that are doing things? And, what about the corrosiveness? What about, electricity? So a lot of different things, some of them, as it turned out, we were able to rule out. But when you're on the clock, you pull out everything. We're not going to read this list to you one by one, other than you probably will recognize them from a little bit from some of your geotech engineering courses and probably some from your chemistry courses as well. But that's just kind of the laundry list of the lab testing. Now, this photo, before we get into the potential causes, this photo is interesting because essentially that solid surface that you see that's at a right angle, that's where the part of the footing settled. So this is actually, if you can imagine, if you ever push down into moist or wet ground and you get that almost perfectly aligned surface, that's what the surface looked like near Pier 22. So as we were going through the testing, that we're starting to zero in on some potential causes. Was it something to do with the piling? Again, we hadn't at that point gotten to that, but we were beginning to have our suspicions that might be an aspect of it. Another, bedrock cavity, which is not Fred Flintstone with a toothache. It's, if you can imagine, an open area beneath the bedrock where, for some unknown reason, suddenly that cavity collapsed, or something with the soils. But again, more to follow as we work our way through this investigation. So on day 3, that alarm that we saw there previously, yes?
Tell us a little bit about how you're starting.
We will. Absolutely. Great question. For those of you online, he was wondering, get a little bit more info about how the pier was constructed. And the footings that will become very important here. So on day 3, we were able to get those alarms installed, and it allowed us to get down in there. Day 4, again, we're down there, we're looking at Pier 22, the epicenter, and they did a test pit. They looked at one test pit, and there's a shot of what that looks like. And in one corner, they went down 3 feet, and it's like, hey, drum roll, this is it. Smoking gun, nothing. Meanwhile, a day later, over at Pier 25, 3 piers away, they found severe corrosion. And they're like, well, wait a second. You know, the pier settled at Pier 22. I'm over here 3 piers away from the river, and now I have corrosion with section loss, you know, with the pile with section loss in it. What's going on with that? So day 5, we also found at Pier 21, pier next door to 22, also section loss. So it's like, okay, what does section loss mean? So if you can imagine this entire pile being whole, that's what's left of it. Kind of looks like an old steel Pabst can that you found buried out in the field for 50 years. But really, you think about it from a construction standpoint, a more serious standpoint, that pile, one of many piles, was intended to exist in its as-built state and extend down into the ground. And now you look at what we have. And so then that chases us back the whole investigation piece further, where we go, aha, we have corrosion on the pile, but what was causing the corrosion? So here's here at Pier 22, if you'll notice how the pile comes down and then kind of bends, basically at Pier 22 itself, it collapsed on itself about 8 foot below the bottom of the footing. So we found that on day 6. And there was 1 pile in one corner and 2 piles in a different, in both of them on the west side, that all failed. And that's again resulting with the Pier 22 buckling. So in terms of what they found in the subsurface, there were 3 different things that made for, shall we say, kind of interesting or unique conditions. The first is porous fly ash fill. What is fly ash? Fly ash is a byproduct that comes from power plants. Well, how would porous fly ash fill, aka byproduct from power plants, get in my fill under the bridge? Where would it come from? Well, it came from the power plant that happened to have existed right near where the bridge was built. Perched groundwater. So what that means is, if you can imagine that you have a solid, say, layer of rock, and typically groundwater would, would go, kind of from the ground and then, kind of rising up and down. But it's essentially, an impermeable layer. And so if at the time when they were building it, if they weren't aware that there were certain layers that were impermeable, it would mean that, underneath the ground, there would be sections that typically wouldn't be going through the same kind of rising and falling of groundwater that you would typically see. The third finding is microbial influenced corrosion. And you're like, well, wait. Microbes, like living things? That means that there has to be something living under there. What would that be? Well, it turns out that in addition to using fly ash as fill, they also used a lot of wood pulp byproducts. You're like, well, that's crazy. Where would they find wood pulp byproducts from? From the wood pulp plants that were right there next to where the bridge was built. So again, built in the 70s. Clearly, we wouldn't today use fly ash or wood pulp byproducts as fill material next to our piers, but hey, it was the 70s, man. So here's another example of the corrosion loss. So again, this is your typical steel pile, and you'll notice with the micrometer, you notice that it kind of comes down. Again, they're particularly above the groundwater table is where we would see a lot of that kind of reduction. All right, so in summary, now that we have completed our investigation, we found that at a minimum, we need to do some bridge repairs. We've looked for those factors and we found them at 21, 22, 23, and 25. So something about 24 did not show, we didn't find those there, but the fact that because we remember number lines from elementary school. 24 is perched right there between 23 and 25. We're like, well, we'd rather be safe than sorry. So we're just going to look at these, all 5 of these. So what does a tier 1 bridge repair look like? Well, first of all, it's stabilization. So it's, before we could really dig into a permanent design, again, at this moment, we didn't know who's next, what's going to happen. And so we wanted to stabilize Pier 22, and we wanted to make sure that it would then reinforce the structure so that we would have no further movement. So we began to look at a support tower design. And so just trying to figure out, well, iron oxidizing bacteria are common in shallow wells in Brown County. Well, thank you, Ken. As an added bonus, this bridge is in Brown County. So a very relevant point. Oh, that one. Okay. So it required a lot of modeling to determine what the right thing was in terms of the design. There we go. Now, after 12 years, I finally have to remember, I can remember without prompting, that DL stands for dead load on this slide. So here's this upper chart reflects what we would typically expect to see. Hopefully for those of you who've had structural design courses, some of this will resonate with you. But when it's in equilibrium, we'll see some areas that will be in expansion and other in compression. So keeping the whole structure in sort of a Schwing-Falk kind of balance. Now, this lower chart, or excuse me, this lower exhibit shows that with Pier 22 is gone, we're actually resulting in a huge negative moment at that location, positive moment at that location, because that's what the slide says, as well as a negative, a huge negative moment increase on the other side. And I'm gonna skip the slide. And here we go. So they did a lot of structures modeling. Did I mention I'm not a structure engineer? And so the results were that everything was within capacity. So even though, okay, so as you've learned, we have this thing called factor of safety that's built into the codes, that's built into the structural design. This is why you do that, so that if you're not 1% off, things are going to snap. So everything was in the elastic stress range, which means, again, no permanent deformation, and we could possibly jack it back in its existing position. Again, more good news. How close were we? If that settlement had been another foot, all bets are off in terms of that. So again, for the stabilization, they kind of zeroed in on a 4-tower concept to basically hold the structure securely in place until we do the permanent fix, as well as to make sure that the people who are doing both the temporary and the permanent fix remain safe. So here's a schematic of what that would look like. And basically, in essence, it would remove about 1/4 of that overall load from Pier 22 and distribute it to these 4 towers in this structure. Now, usually, with construction projects, progress is measured in years in terms of plan development, decisions, processes, lettings, design, finally getting them on construction. This is done in 5 days. Okay, we're going to do a tower. All right, call up 3 contractors. We're going to meet tomorrow in the conference room. Okay, got enough of their feedback. Here's what we think we want you to build for us. Could you get us something back in 2 days? Usually that process I just described is years. This is what you do with a transportation emergency. So ultimately, at a bargain cost of $1.57 million, they came out and they built these temporary towers, and they were able to get it done in basically a couple weeks. So, recognizing that time was money, I mean, certainly that was part of it, but it was intended to be exceptionally robust. So for those of you who have a hankering for a little more detail, basically it was 8 giant steel H piles that were driven all the way to bearing. And, we also had to do pre-boring to limit the vibration. So instead of just pounding it straight into the ground, we started by drilling into the ground because we didn't want to disrupt the underground utilities too much. And it's like, well, no, you never want to disrupt utilities. I mean, after all, what's the worst that could happen? I think I have something here a little later that talks about it. So here they are welding the tower. Oh, it's a fuel pipeline. You don't want to blow up the fuel pipeline. Of course not. So that was definitely a challenge. And so what we'd have to do is, typically if you've ever been out a construction site where they're doing that jackhammer, they're pile driving, the pile drivers, you can hear them going pretty quick. Well, here it was pile, monitor. Okay, are we still good? All right. Pile. Okay, monitor. Are we still good? As you can imagine, it lengthened the amount of time, but it didn't want to blow up the pipeline. So there you go. And it was 15 feet away. So they had to rent a couple 300-foot cranes. So here you see that those are the 4 towers. It's almost Lords of the Rings-ish how it looked. But wait, that's not enough. We also, because again, we're engineers. We want safety on top of the safety. So we also established some lateral bracing at the 5 piers of interest. Now, what did the lateral bracing do? It even further limits the potential for movement in the, in your XYZ axis, and it really binds it together. So it's not, you can't have just like one pier or one component go rogue and start settling. It keeps everything together. And here's what it looks like when it's going down the road. And yeah, that's a lot of pounds. Even if you convert it to tons, that's a lot of tons. So nearly 600,000 pounds in the trusses. So now we're going to pivot to the permanent repair. So we had to look at options. What are we going to do? I mean, we've got it stabilized. Are we going to demolish the entire piers? Are we going to rebuild them and repair them in such a way? And what the smart structural and geotech people came up with is like, we're going to come up with a new foundation system. We're going to do something that's going to last for 75 years. And we're going to do it at those 5 piers that we have interest in. And you're like, well, you're not going to give us details. Well, yes, I am, actually. So this next slide shows a cutaway. If you look at hopefully everyone can see shades here. But if you look at the light gray in the middle, those represent the existing column and the existing footing, and then the piles that extended down out of underneath all of them. And so what the repair is that was come up with is we're going to actually increase the size of the footing. So if the footing was this size, this is pretty exacting. We're going to make the footing bigger. We're going to slope it with a buttress wall up into the existing column. Then we're going to drill holes through the footing, and we're going to use post-tensioning so that the new part of the footing and the old part of the footing are all connected together. And then instead of these, 50-year-old schlats and hams cans sticking out in the ground, we're going to go with 4 drilled shafts down to bedrock. And we're also going to have because we still don't know why the corrosion occurred, we're going to put a PVC pipe around that's going to handle the first 30 foot for all of these. So this thing is not going to move. It'll probably still be there even when they rebuild the bridge. It was going to be that robust of a design. And so here's a cutaway view that kind of looks at that again with the kind of the existing column and footing, and then the expanded as well. So now we're going to talk a little bit, move away from how deep is the bedrock. 100+ feet, and it varies. There we go. All right, so now we're going to talk a little bit about the permanent repair and hit on those topics in the gray box and roll on from here. So 7.72 million is what the cost of the permanent repair ended up being. And so this is a snapshot of the construction scheduling. So in your construction course, you learn about Gantt chart scheduling. As you can imagine, because of these 5 piers, a lot of what we're doing is going to be essentially the same thing over and over again. There was a little bit of that rinse repeat. Now, of course, because they're not doing all 5 piers simultaneously, they move from one and keep rolling on through. So again, here's 21 to 25. They're doing all those things, drilled shafts, footings, and then ultimately culminating with bridge jacking. So if you've ever had like a project where you're trying to affix a new surface to an old surface, sometimes you have to rough it up with sandpaper in order to get them to adhere better. That's essentially what they were doing there with scarifying the piers and footings. So you may recall those columns, we were going to be building those new buttresses. So that was a piece of it. So here's what it looks like when you excavate down to the level of the bottom of the footing. So this is our, who were the, you're going to see that at the very last slide, Richard. I wish I could. Awesome. All right. So on day 43, that, okay, thanks. It disappears, right? Okay, cool. Getting down in the hole, this is after, as they're drilling those 4-inch diameter holes through the footing that ultimately we're going to be doing post-tensioning through. So drill shaft construction, why did we go with that instead of pilings? Well, of course, because pilings will not last. So resistant to corrosion, and it was also less vibration. That fuel line that we didn't want to blow up, it was still there, and we still didn't want to blow it up. So here we are on day 50. This is one of the, at 60 foot, this is roughly the first half of that steel casing pipe. And then here's on day 68 where we're installing this isn't the entire 30 feet, but basically a fiberglass liner around it so that it would never be. So as you recall, we're expanding the footprint of each of the footings. Again, very conservative design solution. We didn't want to leave anything to chance. So there's just a little bit of rebar in there. In fact, one of the comments from one of the contractors that was out there is that, there was by the time they got all the rebar in, there was barely room to move in there because we wanted it. So, no room to move for the person who's in there putting it, and then no room for the pier ever to move again. So as we start to see, this is obviously the above ground, that sort of diagonal buttress that we talked about. There's the cage for that being formed. Below that, you can also see where they've already run the existing for the existing footing itself, how they've established some of those holes for the pre-stressed cable that's going to go through. So by the time we get to day 98, there's a pour, and look, that's what the new buttress is. So just as they were able to do that in a matter of weeks, I'm able to show you from a plan to a cage to a finished project in a matter of minutes. So then, as you can imagine, a lot of rinse repeat work. In other words, doing the same thing on all 5 of those bridge piers. We get to the bridge jacking phase. They recognize that they're going to need to get this done. And as you can imagine, when you're jacking a bridge and everybody is staring at you, you want to make sure that you do a lot of extra planning. And part of that extra planning is that you don't go in and say, okay, let's do 2 feet all at once. No, you jack it 2 inches and you say, okay, how are things looking? Monitoring there at the pier itself, but also up above to be able to demonstrate that. So now I'm going to turn to Danny and say, if I switch to my little 15-second video, we're going to hope that this is all going to work out here. Let's see if I do this. And if I push play, Okay, so I'm gonna run through this time lapse that is not gonna switch. How do I switch it onto? Oh, on the Zoom, I bet. Okay, you know what? Okay, so we're gonna skip this for right now in the interest of time, and we're gonna come back to it perhaps. Let's see here. Ha, good. Little different. All right. So as you can imagine, a lot of equipment associated with jacking up the blocking. And so you'll notice here, there's some, obviously these were some sort of digital cameras that would put orange dates on the bottom. So this was December of 2020 or 2013. The first thing you've got to notice is like, well, that's a lot of snow. It must be pretty cold up there. We'll talk about that. So day 86, we finished the northbound jacking. And then, as you can imagine, once you've jacked it up, you now have this space. And so we had to insert essentially a bolster. So and kind of like a shim. And then, of course, you didn't want that shim to ever get knocked out of place. So welding that all together. And then, so here's another shot of what that completed Pier cap looked like. There were challenges, ouch, related to the cold. So during the last 51 days, so from basically November of 2013 to January 2014, the high temperature during those 51 days, it was below freezing over half of them. And half of them had snow, another 5 days with rain. So if you can imagine like your worst field trip or flat tire adventure ever of being out in the rain, in the snow, in the cold, that's what it was for the folks that were there in the trenches doing the repair. There was a particular cold snap where the highs were down close to zero. And typically they had been, the contractor team had been working 2 8-hour shifts. They shortened it to 1 4-hour shift for that period of time because it was just so brutally cold and unsafe. All right, so now we're in the home stretch of the emergency repair. So we're going to talk a little bit about those things shown in the box. So Richard asked a lot of great questions. One of the things that I think, it's like, why am I still telling this story, right? Why am I still telling this story? For a couple of reasons. One is because sometimes with a transportation emergency, you'll have the opportunity to just go and do. And what really separates this from other, emergencies is trying to figure out, simultaneously keep everybody safe, figure out what's going on, knowing all the time that you're on the clock. The other thing that I think this really represents is it's the power of our profession. We had public sector engineers and other transportation folks, private sector consultants, contractors, the contractor workforce, everybody, marshaled together, no bickering, no egos, just trying to figure out how can we get this done. And so it was really quite a massive effort with a lot of different entities involved. It was obviously, as I think Christina pointed out, apropos, it was in Brown County. So working with Brown County folks, with Green Bay folks. If you don't think a transportation emergency like this doesn't get you attention from the governor's office on down, it gets you attention from the governor's office on down. So from a process standpoint, again, as you get out into your careers, you'll find out how exceptionally long these processes typically take. And so again, just for the permanent repair, again, this is the permanent repair, deciding on a special letting, doing environmental documentation in days, a plan set within basically a week and a half, putting it out to bid and giving the contractors a full week to look at it, and then getting work started on November 1st. It's almost unheard of, but I'm going to say this again. In a transportation emergency, you'll be asked to do things far faster, work far harder, and in order to get things done because of just how it affects everybody. This was a case also where the contractor, an disincentive clause was put on there. Engineers that work for design firms, they put together their best guess of what it looks like, but contractors, they're in the business of really understanding and finding those efficiencies. So we really wanted the bridge open. And so we thought, well, we're going to put some money out there to do it. And wouldn't you know, the contractor finished and grabbed the maximum incentive. And we all said, thank you, because ultimately we wanted it done. So survey was obviously an important part about it, as we talked about. And then there are some random pictures we're going to skip through. We used robots. It was legal. But basically, after a while, we figured out that, it didn't make sense to keep sending surveyors out there twice a day. So we would send, we were able to put up an automatic robotic survey monitor that would do that. So there's the robot right now. That's before it became sentient and tried to kill us. And then we're not going to show the video, but January 5th, 2014, after 100+ days, that same group of high-flying characters came to Green Bay and announced that the bridge was open on day 102. So 15 days ahead of schedule. It was a very cold day. So a few things by the numbers: 27,000 hours were expended by all the different folks who put in together. They worked every day but Christmas Eve and Christmas Day. Sometimes it was around the clock, and sometimes they double crewed because they just wanted to get it done. One of the contractors said he didn't see his house in the daylight for over a month. Again, not hard to imagine as the days get shortest in December, but then there were also those moments where you're starting to do bridge jacking, and you hear this crunching and cracking, and you find out that it really wasn't that big of a deal. Or you've got a room full of the press, and somebody comes in and whispers, the bridge just settled another 1/2 inch or 1/4 inch. So a little bit about next steps, including not only the inspections, but also some monitoring. Okay, so post transportation emergency from 2014 actually to the present, continued to do a bit of monitoring of the piers. And in essence, at these different pier locations, there's a PVC conduit that goes down underground, along with these, with the existing steel piles. And we use these probes and this magic piece of equipment to measure the electrical resistivity, or the ER for short. And so they've been collecting numbers for a while. I'm going to skip this graph. And even this graph is exceptionally confusing and hard to understand, but I'm going to summarize it as follows. So we know what the condition was of the various piers when we were taking a look at them in 2013. And by collecting data over time, we're able to look at the corrosion that we're observing, and then our electrical resistivity information, and we are projecting based on that how long a specific pier would last. And so in the case of one pier, what we find is we'd like that pier to last at least till roughly 2050, 2060. And in the case of Pier 6, the results that we were getting says, actually, no, by 2031, you're probably going to have a compromised piling. Whereas at Pier 13, I should say, it's a little bit longer. And meanwhile, at Pier 50, which is as far away from the river as we can get, we're actually in good shape. So what does all that mean, really? So what that really means is that we recognize that the setting for all of those piers presents a problem. And that for the, as we've continued to monitor them, there's actually a design project underway where they're going to be further addressing what's going on with some of these other piers and bolster them to make sure that there's not an issue. And so now as we approach the top of the hour, photo moment from Danny. Just a few final shots of kind of what it looked like. This was the cold January day. And I want to emphasize again. So I was at, last month, I was at Iowa State, my alma mater, doing this presentation and, talking to a lot of students, not unlike here. If you're a senior, you're not going to the career fair because you have a job. If you're a junior, you had a great internship. If you're a sophomore, you had an internship. If you're a freshman, you've been on campus for 2 months and you're probably going to get an internship. Things are very different than they were decades past. But the thing that I underscored is whether your career takes you to work in the public sector and the private sector for a consultant, for a contractor, there may be a time in your professional career that you're faced with something like this. Not this specifically, but something like that. And that's the time that really, I think, demonstrates the greatest part of this profession and, why we put ourselves and, the people that we work for first, because ultimately it affects everybody's lives. And so then there's just a few more cold things and quick, get a snapshot of this. Here's a few of the many different consultant design firms, PI firms, testing firms that were involved. And with that, under an hour, good. I'm finally learning how to do this presentation, by the way. Any questions about anything that we covered here? Questions?
Though we're a little over 1 hour, but we can do 2 quick ones. Yes.
When the pier settled, did it stay plumb? Generally, yes. It did not, it didn't really move, other than moving in the Z direction and going straight down, it did not have really any perceptible in the X or Y. Question? You're like, no, I'm just leaning.
How much consensus was there among the engineering entities
On
on the whole project?
how much
In other words, how many were there other alternatives to examine before they came on this?
So the question for the folks that I'm gonna get, hopefully, oh, okay, I'm gonna get to his after that. So the question is, how much consensus? During what we'll refer to as the discussion phase, where people are floating alternative theories, presenting pieces of information that would suggest to support it. I think there was a good amount of discussion because there wasn't, there was not like this one aha moment where we said, it's absolutely this. I think as we got more of that information, not just at the one pier, but at the other piers, everybody has eventually kind of coalesced around that specific hypothesis. But even then, the hypothesis was never that it's just one thing, and the interaction of things. I mean, there were folks that were, some of the nationwide firms, I mean, they're connected with universities and stuff. We couldn't find anything that talked about, show me the interaction of fly ash and wood pulp and perched water. Like, it's not something that was ever really looked at. But it was funny because now, the other aspect of it is when I was out in Ames, one of the students who attended said, "Oh yeah, my professor just talked about that in class." I'm like, "Good." So, but yeah, so it wasn't. Eventually, there was that sort of collation on things, but never like 100%. The other question that disappeared from the screen was, how did you pick a consultant in such a short period of time? So that's a great question. And my wife would remind me, remember, Brian, mainly students, keep it in under 2 minutes. Okay. So we have standard processes for how we select consultants using a qualifications-based selection process. And we follow those pretty rigorously with DOT. So it's not like we're bidding out engineering services or anything. So in this specific case, and I can speak to this at length, but Danny says no, so I won't. We knew a couple things. We knew that, number one, we didn't have very much time. We wanted a firm that is really familiar with structural engineering in Wisconsin. So those were like the easy ones. At the moment in time when that structure, when the pier collapsed, there was one consulting firm that was working on Leo Frigo's sibling, the Hone Bridge in Milwaukee. Remember I said there are 3? So here was an engineering firm that was working on its sibling. And at that moment in time, on day 0, we had no idea what we were going to need to do, whether we were going to have to start tearing down stuff or not. And so we made the decision to hire the firm that was working on the sibling, because we knew that whatever it is that we had to do, at least we had somebody who had spent the past 2 years working on that sibling. And that we didn't want to bring in somebody who, you know, again, a lot of great structural engineers, but we didn't want to bring somebody in who didn't have experience working on these type of structures, let alone its sibling. So I hope that answered the question. That's the 2-minute version that my wife told me to use. But I was central to that discussion. So.
All right, so we'll do this. In respect of everybody's time, from 5 to 6, so it's 6:08. We're gonna officially close the seminar, but you are all welcome to stay. I believe the speaker will stay as well, so we can still discuss all your questions until we're all satisfied.
I have 60 seconds for the folks that are in the room.
All right. Well, please help me thank our speaker. Thank you so much. All right, and then I will stop recording, and then we can ask